and start our recording and do our lecturing. Now, this is going to be essentially a continuation of last time. There's going to be some more caveats that we're adding in here. So we're going to do the electrophilic addition again. It's going to be nonpolar pi bonds. This is the second part of that. Okay, so everything that was true last time, still true. I know. The reactions will involve cyclic transition states, though, in this case. Okay, and so we're going to start having this wraparound that we're going to see, right? So we're going to have these very interesting cyclic transition states. That means that they're going to be very analogous to your like SN2 reactions and stuff like that. But remember where we started talking about those, where we have like the double bonded carbonyl, and it has the electrons that get pulled up, but doesn't actually leave? It's going to be very similar to that. We're going to have a leaving group. I'm doing scare quotes because it's scary. But these little leaving groups are not actually going to leave, right? They're going to stay attached to the other carbon. Okay? Okay. You're going to go, Dr. Clausen, did we really need a whole chapter of this? There's going to be points of this class, by the way, where for some of you, it's going to feel like I'm beating a dead horse, and you're going to go, stop it. Unnecessary violence, Dr. Clausen. See, I got a dead horse reference in there. Yep, I'm 30% violence. Okay. All right, so this right here is our Bronsted acid. It's going to donate an H+, and you're all used to that, right? And then we have that conjugate acid portion right here, which is that negatively charged, like a bromide or something, right? And that's going to react typically with that carbocation, because that is an excellent electrophile at that point. These are usually pretty good nucleophiles, and so they react very nicely. This doesn't have to be bromide. It can be many, many, many different things. I actually showed you like, I think 5 or 6 different ones last time. And there's actually more beyond that. It just has to be a good Bronsted acid. There is a whole world of that. All right, now, this right here is going to be what we're talking about for this new one. And so what you're going to have is you're going to have an electrophile here. It's going to have that lone pair. And remember that these are delocalized electrons. They can move around, right? And so this is then going to attack one of the carbons. It's then going to pull the electrons from those delocalized pi bond into a new sigma bond. Okay? And what that's going to end up doing is that is then going to make this cyclic state. If anybody looks at that and goes, Dr. Clausen, that doesn't look very stable, you are absolutely correct. This is not something that you can typically do, like even doing this with the atmosphere as it is, like regular atmosphere, is usually not advisable or particularly effective. Okay? You typically have to set up conditions that are very specific. Right? These things will react with water, they'll react with lots and lots of stuff, right? Anything that makes that fall apart is going to work pretty well because it's pretty high energy. Okay, not as high energy as a carbocation though, so you can actually get this and have it stay for a while. Okay, pretty hard to isolate though, but sometimes you can. Okay. Okay. Anybody remember what the name of those is? If it's like oxygen here, epoxide. Anybody ever heard of epoxides before? Yes. So you can get epoxides, of course. This would be epoxides, so you can make epoxides using this. And then you can have those stick around in a tube, which you would use to do things like glue stuff, right? Yeah. But they do actually react with water, and that's why they have a date on them that says used by. Okay. And they'll fall apart due to light and everything else. They are unstable, but stable enough to stay for a month or two if you purify it and keep it nicely contained and block light and do all this work. Okay. Okay, now let's talk a bit about stereochemistry in these reactions, because these have very, very predictable stereochemistry. Okay, because you're adding across one side, it's going to maintain a ring that's going to keep everything trapped, right? Because the two things that have cis-trans states that we first learned about were double bonds and rings, right? And so, hey, we're going to maintain that, aren't we? That's quite nice. So the cis-trans relationship in this alkene is going to be conserved for those groups that are attached to that CC double bond. The cyclic product is going to be chiral. If the cyclic product is chiral, then the mixture of stereoisomers will be produced because you're flat, right? And you're going to attack from above, but you can also attack from below. Okay. And so you're going to get both of those. This right here again is going to be the 2 and 4 groups right here. Notice they're on the same side here. And so if you attack from either side, what do you notice about those groups? They're going to stay on the same side, aren't they? Because you're not doing any rearrangement here. Everything's trapped. You can't turn before, can't turn after. No, they don't have to be the same R groups. So like this could be a methyl, ethyl, propyl, in which case it wouldn't be the same thing anymore. This would be here. So if you were to go like this and flip it, the 4 would be where the 2 is on this one. Does that make sense? And you can try it with your hand if you want. Like this. See, that's opposite. Yeah. Literally handed, right? Yeah. And so that would give you your 2 stereoisomers right there. Now, keep in mind that they are going to be on the same side if they were previously on the same side. So it makes it very, very convenient to draw these out and figure out which of those you have. Okay? As long as you remember that caveat. Okay, so let's talk about carbenes real quick, because we need to understand carbenes while we're going through this. So right here, we have what's called a carbene. It's not going to have an octet. It's going to be highly electron deficient, but it's also not charged. Okay? So it's not going to have a charge. So it still has 4 electrons associated with this. Okay? And so what we're going to see here is it just doesn't have the extra bonds. Right? This right here is going to give you what looks like this. So you're going to have an empty p orbital, and then you're going to have this lone pair. This is going to occupy an sp2 hybrid orbital because it has electrons in it. And so it's going to give you your maximum separation like we had talked about before, right? And so this is going to be trigonal planar in geometry, but it's going to have this empty p orbital hovering above it, which is an empty space that nucleus can pull electrons into very easily, right? And so these are very, very highly reactive species, okay? Very reactive. Previously thought that they could not exist in any environment with water. Does anybody know what happened recently that has like shaken the carbene chemistry? No? You guys ever heard of the vitamin, I believe it's B12, remember correctly? Recently, they found out that that vitamin actually has a carbene. It's maintained by a hydrophobic environment, and it maintains it in water solutions in your body. So you have carbenes in your body right now. And they're just floating around, and they don't react with anything because the water can't get in to get to them. So it's pretty awesome, actually. Big deal. That's one of the reasons. Another reason now why I can't just be like, this is the rule, and it can't be possibly be violated. Because every damn rule. Huh? So technically it was only 2 last year, because one of the ones I told you about was actually October or November the previous year. So, but yeah, they also found out that you can do, somebody proved, UCLA, I believe it was, that you can put double bonds on bridgeheads, which we'll talk about a bit more. Get more. Okay. So a carbene is going to contain 2 bonds, lone pair of electrons, empty p orbital. Okay. Pretty similar to a carbocation in many ways, just not positively charged, right? This being analogous to a bond. Again, it's going to lack an octet. You're going to be electron deficient, and so you're going to want to take on electrons. So the biggest difference here is that carbocations are positively charged, right? Carbenes are not positively charged. Okay. The formal charge is 0. They are neutral. And so, for example, that vitamin story just now actually gave you kind of a hint of something. They're neutral, right? So they can exist in nonpolar environments very well. Okay? They will very happily exist in nonpolar environments, and it will actually be one of the ways you can keep a carbene, because the law of nonpolar stuff doesn't react with it much. So they are highly reactive. These have to be generated in situ from precursors typically. They cannot just be like bought in situ in solution in the environment you're going to use it in. They cannot be just purchased from like a manufacturer and then, hey, you got carbene that you can do. Okay. You have to make these so that they can be used. So this, for example, is one way to make a carbene. Right here we have this compound. We want a carbene because it's a very reactive carbon. This will make a propyl ring. That's a semi-stable 3-member ring. Mostly stable, except under fairly high like light conditions and stuff. You put this outside in the UV and oxygen and stuff, probably not gonna last. But this right here is going to be a high energy light, by the way, in case you're wondering. This could be blue light or it could have to be UV light. Okay, it depends on how high energy it has to be, right? But it's a common way to like start a reaction, make something that's semi-unstable, break apart. Okay. In case you're wondering, it's the ozone layer depleting, CFCs. In case you've ever heard of any of that, that's why that happened. Is because scientists didn't play around a lot with UV light because they didn't have UV light sources that were common. Now we have UV light sources that are common, so we can test that. But this is your new ring right here. It's cyclopropane because you're going to do a reaction just like we talked about before. Notice on that carbene, it has the 2 elements that we were looking at before, right? And so it's an electrophile. This right here has an empty p orbital, and it has a lone pair that can do the other attack, right? And so we have all the pieces now, don't we? And so what we're going to get here is this right here is that compound that we just saw that we're using as a reagent. This is stable enough that you can get it and you can purchase it, okay? Even though it looks pretty crazy, right? It's a nitrogen triple bond, in case you're wondering. So this right here, you're going to hit it with high energy light. This is going to cause this fairly weak bond right here to separate. The nitrogen, because it's positively charged, is going to end up taking those electrons right there. And so that's going to leave you with a neutral carbene. And that's because this is normally has a negative charge when you do assign the formal charges to this. Okay. This right here is your carbene then. And so what's going to happen is your lone pair is going to attack one of the carbons, and then this carbene has that empty p orbital that's going to pull those electrons from that pi bond into the new sigma bond. Okay? And that's going to give you this structure right here. And so this was the heterolysis, lysis breaking a bond. One of the species takes the electrons, right? And then we're left with our carbene. The carbene is then going to be the electrophilic addition. Okay, an electrophile adding addition, right, across a double bond in this case. Okay, a pi bond. Okay. Does anybody have any questions? Okay. In case you're wondering, this right here is called a diazo group. Okay, so if you ever hear diazo, that's what that means. It's a nitrogen-nitrogen triple bond that is bonded to something else. Okay, nitrogen-nitrogen just triple bonded. That's it. That's 71% of the air. Methane then is diazomethane, methane right here, of course. And that is an explosive. It requires extreme caution in laboratory. This can go off pretty easy if you let oxygen in, if you, not oxygen, excuse me, the atmosphere in with like water. This will go off pretty easy. Okay. So you have to be very, very careful with diazomethane. Obviously, if you shine high energy light on it, it'll start reacting too. So there is also that concern. Now, this right here is some different reactions, including epoxy. So this is going to be the epoxide right here. This can be produced from an alkene. Peroxy acid is one of the most common ways of producing this. That's going to be where you have some group attached to a CO3 and then one hydrogen on there. It's kind of like a carboxylic acid, but you have more oxygens. Okay? And so you're more acidic and more reactive in general. Now, this is called a peracid. Per, if you remember, do you guys remember your like chlorates at all? Hypochlorite, chlorite, chlorate, and then perchloric, right? And so per is the way of indicating you have additional oxygens beyond one of the more oxygenated states. Okay? It's usually the highest oxygenated state. And they start using that when you have like 3 oxygens, that sort of stuff. Okay? Okay, so this is a very, very common peracid right here. This is M-chloroperbenzoic acid. This is what that looks like right here. Okay. See the peracid right there, the additional oxygen. Okay. This is why it can easily react stuff and put an oxygen on things, is it has that oxygen and oxygen double bond. You'll notice it looks a lot like something else. Anybody want to try that? It makes an epoxide, but if you wanted to bleach your hair, what would you use? Okay, bleach being one. Actually, bleaches, a lot of bleaches are like this as well. Hydrogen peroxide, peracid, peroxide has the oxygen double bond, oxygen bond. People do sometimes use hydrogen peroxide to bleach their hair, low concentrations, of course. Yeah, it is bad, but fairly common. All right. The abbreviation for it is MCPBA. Okay? And that's where you know that you have that's going on. What ends up happening is this is going to go to the carboxylic acid when it loses its oxygen. Okay, so let's look at what happens when you actually do this reaction. So you'll notice that you have this carbonyl next to this peroxide group, right? And so what you're seeing here is that it's actually going to make a hydrogen bond in on itself. Because how many atoms are in this ring here? That's one of the stable rings, isn't it? And so it comes back around, makes a hydrogen bond. That hydrogen bond's a little bit longer than these other things. And so that hydrogen very easily can jump onto the other oxygen. Okay? And so what's going to happen is this is actually going to be your electrophilic species that's going to attack here. You're going to have that lone pair of electrons, this electrons here. This is a simplified mechanism, by the way, that you can actually rewrite this mechanism in a more complicated one. But you can have these electrons right here. They're going to attack that carbon there. And then the delocalized pi electrons here are going to get drawn up on that oxygen because it's losing electrons, right? This is going to have a cyclic, like where electrons jump one after another, right? And so what you're going to see is this hydrogen here, right, is taking electrons from that carbonyl. So the carbonyl is going to pull electrons away from the carbon, and that's going to leave the carbon as a deficit, isn't it? And so then it's going to take the electrons in the oxygen-oxygen bond. oxygen and oxygen bonds aren't super stable. Okay, it's one of the reasons why oxygen is so reactive in general, right? It is not in that nice spot where it just is very, very stable. All right, this in particular is quite unstable because of this shape that it takes on, where it has that proton that's very easily can just flip over from one to the other, okay, which destabilizes that bond. Okay, that's going to leave you with the epoxide here. This reaction is what is called concerted. Once you start any part of this, it's going to cause all the other parts to go. And I know that I tend to talk about these as if one causes the other, but if you flip that around, it would have been caused by the other side. So if we talked about this attacking here, this is going to weaken that bond. That weakened bond is going to start moving over and attaching to that, right? And so each of these causes the other, right? So it is a concerted reaction. Everything takes place once. The nice thing about these is you avoid carbocations, right? Whenever you have a carbocation, what do you know about that carbocation? Well, first, carbocations are very, very high energy, right? And so you can get hydride and methyl shifts. That's a problem, isn't it? If you get rearrangements, you're going to destroy your structure, aren't you? The other part that's a problem, though, is when you make a carbocation from a double bond, what do you lose? Your geometry, don't you? Your trans cis state all of a sudden becomes a one bond and can freely rotate around it, can't it? And so you lose that geometry. By keeping this as a concerted mechanism, much like an SN2 reaction that we were talking about back in the day, we can keep that as all in one step. We can keep that geometry. We don't have to lose the geometry, okay? And this will maintain that geometry, actually. You can actually see that maintained geometry right here. See that? This is not normally how you write a double bond, by the way, where it's coming out towards you, right, for those groups. Normally you write it so it's going down. Yeah. But that is more easily seen what happens with the triple, the three-member ring. Okay, so the peroxy acid as a source of uncharged oxygen atoms, we can actually abstract these peroxy acids and sort of think of them as a source of these neutral oxygens, okay? You can actually generate neutral oxygens in situ as well. We'll kind of talk about a little bit of that. It's pretty, and I'm not going to say any more about that right now. Let's get done with what we're doing. Okay, so this is a very easy way if you don't want to decide. I'm going to use MCPBA. You just want to keep it I'm going to use a source of oxygens. Okay, there's 20 or something different sources of oxygens I could use. I'm not sure which one I want, right? And so you abstract this as a neutral oxygen, just as it would be on the periodic table with no reactions of anything. Okay. Now note the periodic table one is actually a diatomic gas usually. This would be actually as stated on the periodic table. So kind of an interesting thing. Back in general chemistry, when your professor was like, that doesn't exist. There you go. It kind of does exist. It's just super high energy. Now, that peroxy acid that's going to serve as a source that will donate these oxygen atoms to our alkene, we can think of that peroxy acid as a source and just remove it from our mechanisms, remove it from our thought process here. Okay? And so you still have a concerted reaction. It's just neutral oxygen that you have to consider. And so you get the epoxide, same as before. Notice that in case of our products and what the resulting geometry is, it doesn't matter. Yeah. And this is one of the ways you can really help yourself out in organic chemistry and in general, anything that takes mechanisms a lot. You can abstract the species you're using. For anybody that's going biochemistry does this a tremendous amount of the time. Many of the enzyme states that are listed as just the short cycles or pathways in those books are not as listed. Okay? They are, in fact, abstractions of the actual species. Typically, you have to have like a substrate binding, and you have rearrangements, and you have changing of geometries and energy states, and so there's actually a lot of stuff going on. Now, let's identify our missing components. We want to identify the missing component that should be in A, B, and C. And so you all will want to discuss, argue, and try to work this out. Remember, you got to commit to these, right? So don't forget to commit. You got to write it down. Because, most of your thinking is actually just justification of gut feelings you popped out. When they took high speed measurements of brain activity, what they ended up finding out is people like just pop out answers. A lot of it comes from the silent part of your brain that does not actually like think things through. And then you spend like a couple seconds justifying that answer to yourself. This is why I did that. And that reasoning usually has nothing to do with the actual why. Which is just wild. I like saying we're puppets that are controlled by our gut bacteria, mitochondria, and the two silent parts of our brain. And we just like justify our strains. Oh, I meant to do that. Okay, I'm going to start going on. I think everybody has at least an idea what they're committed to. Okay, so we kind of have to go first reaction, second reaction, third reaction, right? Though we know from this one right here, we're probably looking at some sort of double bond here, aren't we? And we're looking at epoxide on the other side because, hey, I recognize that from the thing we just talked about, right? So, what happens to an OH when you have a strong acid in there? It's going to protonate that OH, right? When you protonate that, it makes a real nice leaving group, doesn't it? Yeah. And so you're going to get your nice elimination here, make that double bond. And so we made the double bond. Everybody remembers what the triangle means, the delta? Yeah. So strong acid, concentrated strong acid, and then in the presence of heat. Yeah. You may know why we use phosphate here usually. Phosphoric acid. Typically, the reason we use phosphoric acid here, exactly. If we used like HBr, we'd have exactly. Yeah, it's just a hydrogen source, an H+ source. Yeah, got it. Perfect. Okay, and so we go on to the next part. This is those per acids, right? And so we're going to have that peroxy, or another way of saying that we have an oxygen source, right? Neutral oxygen source. So we can do that epoxide reaction. Okay. And then this is just solvent right there. And so we're going to get the epoxide right there as B. And so the last part here, we're going to put a base in here. Okay. And that base, that's going to give us that electron pair on there, right? We have that OH minus there. Then we have water that can do this. And so this is going to be that next reaction right here. You'll remember these reactions from the end of last semester where we were doing like the epoxides and we had the alcohols coming on them. Okay. And so this right here is going to be where we get the alcohol on. And so what's going to happen is we're going to attack from one side. We're then going to get the OH on there. And then we're going to donate a proton onto that other side that ends up coming out. Why can you do that sort of stuff? Or what reaction is this very similar to? This would be like an SN2. So this would be a SN2, but our leaving group doesn't actually leave, right? Okay. So this right here is going to be molecular bromine, and this is going to give you an anti-addition across the CC double bond. And so what we're going to see here is we're going to add one to one side, and then the other one's going to add to the other side. Okay. Now note, because you get the anti-addition, you're going to get our trans conformer. Okay. If there's a difference because of the geometry, like one being one direction, the other being the other direction, if that creates a asymmetric system, we're actually going to get both forms, because which direction we start with is 50-50. We can end up attacking from either side 50% of the time. Okay. I will note that there's actually a lot of these reactions that can go backwards. Okay, just a little, not much. So they're still represented by forward arrows here, but a lot of these reactions, if their energy barrier is not high enough, can actually go backwards fairly easy. Anybody know where famous thing happens with that? Hydrogenation. So have you ever heard of like hydrogenation can create cis trans fats? That's actually that reaction going backwards when people do it. Typically use hydrogenation to give you your saturated fats, right? So it wouldn't give you a cis trans fat. Okay, so this right here is going to be, again, that double bond. This is going to be the bromine. And so one of the reasons why the bromine, this happens a lot, is because they're highly polarizable, because they're so big. Okay? The bigger you are as an atom, the easier your electrons can shift around, right? Or another way of thinking about that, if you have a lot of things that are loosely attached to you, they can easily move around and blow around, right? Okay? And so the electrons are very similar. This happens due to random chance, but it can also be initiated by something else coming along. Okay? So if you have an electron-rich pi bond that comes near, what's going to start happening to your electrons in the bromines? They're going to move away, right? Because they're repelled. Okay? Remember, this is not going to get repelled because it is moving this direction for a reason, right? It has momentum behind it. And so it's going to move those electrons away. That's going to start revealing the protons, right? So you'll start revealing more positive charge. Well, as you get more positive charge and it starts overlapping with this pi bond, right? What's going to happen? You can pull on it, right? Okay. And so what you're going to end up getting is you'll start initiating your bond. It'll start attracting the nucleus. Okay? And so, remember, when isolated, bromine is not electron poor. In fact, bromine is, two bromines. Normally, they would not be electron poor on either one. This is going to be a phenomenon that you're going to see some more of as we go along and we start talking about metals and other things. And it has to do with the fact that the more polarizable you are, the less tightly you hold those electrons, the more easily they can be shifted over. And when they get shifted over, that positive charge doesn't move, does it? And so it reveals positive charge. Okay? And I want you to have that framework in your head. Right? Now, the electron-rich pi bond is going to repel your electrons on one atom of the bromine, of course. This gives you your revealed positive charge. And then you'll get an electron-rich side that's the other side. Okay? And so this will become electron-rich over here. Okay. Now, one of the other things that helps this out is bromine is a great leaving group, right? Bromine, being your leaving group, is a really good leaving group. Okay? It has that sort of magical consistency that's sort of in between, where it can act as a really great leaving group, but can also still act as a nucleophile candidate. So right here, we're going to get that first. They're coming together. We have our double bond coming together. It's pushing those electrons away. And so that's going to start pulling electrons from that pi bond, right? On the other hand, because we start pulling those electrons away from one of the carbons, that carbon's going to start pulling on electrons that are nearby. And so that's going to pull electrons from that bromine. Because, bromine still has 3 lone pairs. It's it's not. It's electron deficit because those electrons are moving away. Only on one spot, though, right? It's only local. Okay, and so that's going to be that electrophilic addition. Now, one of the unique parts of this is it is going to have a leaving group, which is the other bromide, and that's going to pull those electrons from the bond and leave as bromide. Okay, and so you will have created bromide into your system. This is going to leave you with a bromine that's attached to this ring. One of the things you need to keep in mind is because the leaving group leaves with a negative charge, that means the bromine that's attached has to have what charge? Positive, right? You can't create or destroy charges, can you? Because those would be creating destroying electrons. Okay? And so the bromine that's left is going to be positive. Okay? Now, this is going to make both of these sites pretty electrophilic, isn't it? Okay? They're going to have a little bit of positive charge on those sites. And so we have a very traditional sort of SN2 reaction again, don't we? And so we're going to get an SN2 reaction attack. Again, we have a pretty good nucleophile. And then we have positive charges on these carbons, and we're going to get attacked. And that's going to cause the bromine that's attached in both places. Well, it's going to take the electrons in one bond, but it's still going to end up being attached to the other, isn't it? Okay. And so that will give you attached. Notice it's anti, meaning one is on one side, the other's on the other. Okay. Whatever side you originally attacked from, that's your first bromine that stays there. The other side automatically then becomes where you have to do the SN2. Okay. Right. So let's go ahead and try that out. I want all of you to initiate and do this now. Okay, go ahead and go forward, since everybody seems like they are not actively pursuing something. Okay, so we have that double bond, right? And so we're going to do the anti-attack. Notice that we are going to have 4 more things around that central carbons now. And so that is going to have chirality. And so we are going to get the 2 forms. One we're attacked from above, one we're attacked from below at the beginning. Okay? And that'll give us our 2 forms right there. All things being equal, we'll typically get a racemic mixture. But if we have a anti-symmetric environment, right, we can end up getting preference for one. Okay, so let's talk about chlorinium. This is going to be the chloride doing a very similar mechanism. It's going to undergo addition to alkenes. It'll produce what's called vicinal dichlorides. That's vicinal dichlorides, by the way. Vicinal vicinity. So the carbons next to each other. As opposed to geminal, which means twins, right? On the same carbon. Yeah. Okay. And so right here we have this double bond. It's going to go addition across it with the chlorides. In this case, we're going to get about 73%. This is going to give us a meso compound, actually. And that's because we have the same groups on both sides like that. Okay. Okay. And so this is what that looks like in terms of the bromide. Bromide can add to an alkene by both the syn and anti additions. And so this one here would be this first one. We have right here one equivalent, so it's a 1-to-1 ratio. The triple bond is going to be easier to react with. And so we're going to get reaction with the triple bond first. Okay. And that will give us the anti here. Okay. And then this is going to give us the syn for the other one. Okay. Notice the anti is the preferred conformer. It's the more likely to happen. The syn, on the other hand, is the less likely one. Okay. It's the 19% minor. Okay. So we have our major here. This right here is with excess Br2. If we have excess Br2 and we keep our reaction conditions, bless you. Exactly. We get saturated. And so Br is everywhere for everyone. All right. All over the place. Okay. So let's go ahead and look at this mechanism right here. So if we have a triple bond, we have a bit of an issue here for our mechanism, right? And so this would be called the bromonium. I am just like off today. This is what happens when you have me lecture at 8. Bromonium. Thank you. Jesus. I need more coffee. I need to bring the coffee with me. Yeah, I do. Oh my god, I need a lot of coffee for Wednesdays. So this can't be produced right here with an alkyne because you're going to have an sp2 hybridized carbon atoms. These would be too strained to actually exist because remember you have that double bond, right? And so you'd have to have this instead of like this, right? It's going all the way over here. Yeah, if you use the wrong SP. So this just can't exist. You can't get the halogenium state. You saw what I did there. Halogen. Okay, nobody appreciated it. Chemistry joke, falling again. No. That was nice of you. Okay, so if you use water as a solvent, this will actually give you the anti-addition of the water instead. Because the water also can fill this. If it's the solvent, it is going to be, it can do an sp2 reaction, SN2 reaction, excuse me. And it will be in far greater quantities than the bromine. Okay, bromine water being a very, very common substance you can buy, actually. Now, this will give you the anti-addition with the respect to the Br and OH. This is called a bromohydrin. If you had chloro, it'd be chlorohydrin, etc. Okay. And so this is chlorine. If you use water as a solvent again, you're going to get chlorohydrins, very similar to what we were talking about before. So this is actually the mechanism for this. And what you're going to see here is you're going to get that same first step. And so we'll set up the bromonium, here. Thank you. I am just like, my tongue can't make the shape today. You're going to get the electrophilic addition for the first step. Same intermediate again, very high energy. They fall apart extremely easily. Okay. Now, notice that because the water is the solvent, it is going to be far, far more than the bromine, right? And so the bromine is not going to have a chance to come back before water would take its place because they're going to be everywhere. Okay. And so that's then going to be the one that does the SN2 reaction. This is going to give you this one, which is that H2O plus. The waters can't actually do this first reaction. Yeah. Exactly. Yeah, you can have the double bonds in water and it won't never do anything unless you have extremely high energy conditions. Or acid. Acid would help. But just normal water would not do anything, and so it just waits around until bromine comes along. Mm-hmm. But once that you start this and you got the high energy intermediate here, then it can react with the water because high energy intermediate. By the way, this was part of the reason why I was talking about like dry reactions and you have to dry these things. And yeah, water can do a lot of reactions if you get it to high energy intermediate or a high energy state in general. Okay, and so we make that same H2O plus state that we've talked about before. This is an acidic proton, and so the rest of the waters are going to take the acidic proton, and we're going to get our proton transfer to finish this off. Okay. Now remember that Br minus, even if you have a better nucleophile, if you have a high energy state like this, and you have a solvent that's a nucleophile, it's going to be this very same thing as like that solvent leveling effects that we talked about and the various different solvent effects where it's just going to be the solvent reacting with everything because the solvent is in, usually 100 times the concentrations in most of these things, right? We have tens of times at least, usually hundreds of times for most of the stuff. So the solvent just ends up being so much more abundant. Now, these right here, if we put another group here, like a benzene ring, this is going to make these two carbon atoms distinct. And so that will make that system asymmetric. Okay? And so what we're going to see here is that's going to give us some regioselectivity, right? And so instead of getting an even split on these, we're going to get 78% where the bromide goes to this side, and we get the hydrogen part, the OH, on the carbon next to the benzene ring. Okay? And again, that's because that's unsymmetric across that double bond. It is again because the alkene carbon atoms, we have two possible constitutional isomers that are going to form. And this is actually what these states look like. So remember that first state we're forming, right, is the electrophilic addition, and it makes this positively charged three-membered ring. So when we make that positively charged three-membered ring, that positive charge is not just on the bromine, right? That positive charge, because the bromine's pulling electrons away from those carbons, is also on the carbons. Now, which is the most stable place for the positive charge to be? Right there, right? Next to the benzene ring that has lots of delocalized electrons on it. Okay? And so that's going to be your big positive charge on that ring. And so when the oxygen comes along, that's going to be the place that has the most baric orbital with the most positive charge pulled in. Okay? And so that's going to be where the water gets pulled in and makes its bond. All right. And so we get the majority of this. Can it just happen to hit this? Yeah, of course, yeah. It's just going to be more of those are going to get rejected. Okay? Less of these would be rejected. Okay, so this is the oxymercuration reaction. This is oxymercuration reduction reaction, And so this is going to be an addition of water across these bonds, okay? And so, again, recall, H2O can add across a double bond. It usually does this in the presence of a Bronsted acid catalyst, which is what we mentioned before. And so if we give this acidic conditions, we can set it up to add the H2O across. Notice that that catalyst gets regenerated at the end, though. Okay. Now, remember, though, you're going to make a carbocation in those cases. And can everybody tell me why the OH popped up over here? Yeah. We got a rearrangement, don't we? Okay. And so this is going to be your oxymercuration reduction. Notice what we did not get. Yeah, we got them across that double bond, didn't we? So we managed to do it without the rearrangement. It's a miracle. So this is going to have some pretty interesting conditions for these. So again, this is an alternative method that can keep your geometry, okay? That can give you not rearranging into a different constitutional isomer. And so this will add water across the double bond. It's called oxymercuration reduction. Now, the older name, and I haven't been seeing this as much anymore, so I'm not sure if it's still in favor, is the oxymercuration demercuration, okay? Because you're going to put the mercury on, take it off, okay? This is going to have these conditions right here. And so this is actually your source of mercury right here. This is going to be the water and THF. And then you're going to have a second cleanup step where you have to get a negative hydride source. Okay. And then that's the sulfur. All right. Now, two of the sort of important aspects of this reaction that are noteworthy here is the product is going to be the one that's expected from the Markovnikov addition of the OH. So you notice here the hydrogens go with the hydrogens, the OH goes with the more substitute side. That's the Markovnikov. Okay. And the rearrangement generally does not take place. Could you find something that rearranges? Yeah, you probably can. But generally, rearrangement won't take place. This will conserve the geometry. So this is that mercury right here. Because of the rearrange, the carbocation. So the first one, this one that we do right here, in the presence of the acid, the H plus is what attacks first. And then we get the carbocation. And the carbocation then is going to cause the rearrangement. And so the carbocation is the one that causes that hydride shift. And causes the carbocation to be here. And then the water will attack that. Anyways, you can always go back in the chapter and look at that exact same reaction up. Or come and talk. Okay. And so this right here is going to be, these are acyl groups, the same as you would see on like biology. Yeah, I know. So these are acyl groups on the mercury. Yes, mercury binds acyl groups quite nicely, actually. And this would be one of the more poisonous forms of mercury. Actually, mercury metal is not very poisonous. It's quite benign as long as you don't get in your lungs. So right here, we're going to have the HgO8C for the acyls. This is going to give us this mercury that has quite a bit of the electrons pulled away from it by these oxygens here. Okay, but one of the important things is when this leaves, it's going to give you that same resulting carboxylic acid carboxylate ion, right? That's pretty stable. Okay. And so the mercury is actually going to be what does the electrophilic addition. It's going to make the merconium ion intermediate. It's another high energy state, but low enough energy that we can make it, okay, and set it up. Now notice again, water is a solvent, and so water is readily available. It's going to do the attack. The side that has the more positive charge is going to be the one that attacks, and that's always going to be the more substituted side. And so this is why you get the OH at the more substituted side, which is the Markovnikov. Okay, And so that's your SN2 attack right there. That's going to give you the H2O plus, which is very acidic, right? And so we're going to get a proton transfer to the rest of the water. That will give you this species right here, which still has the mercury on it. Okay. That's not super unstable, by the way, but it is going to end up having this NaBH4, which is a hydride source, and we're going to attack it with that because this is a leaving group. It has these oxygens pulling electrons away, and it's fairly stable when it leaves. And so if we provide a good nucleophile to attack, like hydride, which is a good nucleophile, it is going to do the demercuration portion. And so it's going to attack here in a very similar reaction to an SN2 style. It is not a direct, like, this is one step right here, but you don't really need to know all those steps. It's not that important. And so we're going to kind of skip them for now and put a bookmark there, okay? The important part is you're going to get the hydrogen here, and this is going to leave. Okay. I know that oftentimes these are written on the opposite sides of each other. Is there any meaning to that? No. No, it's a single bond. Freely rotates, right? No. Anybody have any questions about that? Yeah. And that's the Markovnikov product that we got. Okay. And so even though the oxymercuration takes place with the anti-addition, any stereochemistry straight up by the oxymercuration is going to be scrambled during the reduction step. This is going to give you a mixture of both the syn and anti-additions of that water. So you don't, yes, it maintains it up to here. But once we get to this next step, we have a single bond, right? And so this can freely flip back and forth. Okay, so this is going to end up scrambling those because we don't maintain that through the entire thing. Okay, the previous ones, when we made that three-membered ring, we maintained it until the other group went on, right? Yeah. Okay, and so we will get the enantiomers. We will not get fully determined stereochemistry here. Okay. There is regioselectivity, but not a determinate stereochemistry. But what do you notice we don't get? What did we never make here? Never made a carbocation, right? And so rearrangements can be pretty difficult to rearrange, isn't it? Okay, because we'd have to rearrange through that three-membered ring. Okay. And so very useful for that. Now, the alkynes, the triple bonds, these can undergo Markovnikov addition of water via oxymercuration. This is actually what you're going to get here. And so we're going to do this portion right here. And that first part we're going to get is going to end up being an enol. Okay? And what do you remember about enols? Not stable, right? In the presence of water, especially if you have any sort of acid or base, you're going to get enol rearrangements. They're going to be extremely common, very common in biology, by the way, biochemistry especially. That you're going to see tautomerization, which is that enol rearrangement. It has a special name because it's, an actual reactions. It has external stuff that has to come on and come off. And that's going to give you the keto form instead. And so you won't stay in the enol form. So again, it's the Markovnikov addition. Hydrogen goes on the less substituted side, the more hydrogen side. The OH goes on the more substituted side. Again, enol's form tautomerizes to the stable keto form. That's the ketone, right? Okay, let's talk about the tautomerization and hydrolysis of your mercuric enol. Excuse me. This right here is the mercuric enol. What you're seeing here is that species that you would have initially made. Notice it has the OH on it, has a double bond, so it's an enol. But we still have that mercury group attached. We have not done the hydride, right? Okay. And so what you're going to see here is this can actually tautomerize. Okay? And so we can get a kind of interesting behaviors here. Right? So one of the ways we can do this, instead of using a hydride source, we can avoid that, which is nice. That's very expensive. It's not super stable. You have to buy it fresh all the time. If you can avoid it, that would be nice. We would not want to, we never get hydride here. You're never going to see it in the labs here. We wouldn't be able to use it fast enough to make it anywhere near, and it's very expensive for us. You guys would have to pay more. I don't want to do that to anybody. Now, this is the merconium ion again. That's going to undergo, it's going to open up. And what's going to happen is it's going to produce the mercuric enol right here. This is going to then tautomerize. That's the tautomerization. Remember, those can go back and forth, but favors this side. And this is then going to be hydrolyzed by the water. And so what we're going to get here is we'll get the keto form. This is going to take that double bond here. And what we're going to see is that this is then going to have if a H plus comes on here, this would cause that to be positively charged, right? And this would pull the electrons in here. And so that's going to pull the electrons away from that mercury, which is a metal, right? So it's going to be a fairly good leaving here. And so that's going to just directly give you your enol form. No hydride necessary. Cool. The enol form then can very easily rearrange to the keto form. And so we'll get that same results. Just no hydride necessary. Okay, so this is some more examples of ketones from alkynes. This is a mercury 2 catalyst that you're using here. So it's mercury with chloride on it. And this can again give you your ketone form, 82%. This is going to be water in the presence of mercury sulfate and sulfuric acid. You also typically need some acetic acid to finish this thing off. And this again is going to give you your keto form. And notice whenever we do these Markovnikov addition on the terminal alkynes, it's always going to produce those ketone forms. Oh, I'm out of time. We'll start up here next time. You all have a wonderful day.